All right, yeah. So we're gonna be doing like some of the Unit 6 problems. So I'll just add the problems in here, and then we'll go from there. So first of all, um, first question has to determine the methods for which theorem one. Uh, the existence of a solution in that interval, and then obviously it says there's some more, but let's just do like 1A first part. 1A. So it's this sort of so it's this equation right here, which is just B doesn't solve it, but let's just think about how we can solve this problem to start with. So on page 343, obviously it goes over this theorem. It's very important, which is that if blah blah blah, if they're all continuous on interval, then there exists a unique solution. So we need to basically find the discontinuities and basically just say those are the intervals. So I can just say, like, for example, here's an example. We'll just do this little paragraph. We'll say um since p1, sorry, since p since ln of x um so since ln of x it'll take a second for it to update because this is probably not the most efficient way to be doing this, but I could also have it auto compile later, but it's fine. I think this is a fine way of doing it for now. Since ln of x is greater than is sorry exists, uh, oops, you have to do. It's fine. I'll just do ln of x. So since ln of x exists only where, so obviously since ln of x exists only where um, there's some certain conditions which are following. So ln of x is equal, so it only exists where x is greater than 0. So let's just write that out. Um, only where obviously x is greater than 0. Uh, and all other coefficients are continuous for all real numbers. The existence of a solution is only guaranteed for um, x is greater than 0. Okay, very nice, I guess. So we've solved this one out. And I think it's pretty elegant, I guess. I mean, not really. Just really the application of a theorem. I don't think we need to do 1B, so let's just move on to a different question because it's kind of boring. So exercise 2 is determine whether these are exercise 2. Um, oops. Determine whether these given functions are linearly independent. So obviously we just have to determine whether these functions are given independent. So what function do they give us? Well, that's a good question. It's a pretty exciting function. It's this function right here, not ln of x. Sorry, 1 second. It's a function called, so it's a solution set. So we'll just we'll just put that in here. and it's e to the 2x. Should probably put parentheses there. X squared e to the 2x. And finally, e to the negative x. Should appear on your end as well. It didn't exactly. There's a slight error with the rendering, so I'll fix that right now. Should be fixed now. Yeah, it works, but it's a little bit scuffed actually. I think I put an extra parentheses here. I don't think I need this parentheses. Do I? No, I do. Oops. Okay. Yeah, I do know. I'm doing that parentheses. Okay. Actually, how do you Okay, this renders a little bit weird, but I think we get the point, right? So how do we do this problem? Um, so the best way to do these types of problems are is take the Wronskian of all the solutions. So I guess let's do that. But I don't actually know how to do a Wronskian late yet, like LaTeX. So let's check that out. Wronskian LaTeX. Question observes. After this question, I need to investigate like why does the Wronskian guarantee independence? Like we need to figure that out. Yeah, like that's very important. So we'll do that right. We'll do that right after this. So let's first observe the Wronskian. So obviously W of some coefficients. So it's gonna be all these solutions. So it's gonna be e to the 2x. Uh, let's just check if I did this right. I just let me just Google how to do e to the 2x well. There's like some weird formatting errors with my parentheses. So I guess we can be doing that. Actually, nothing's loading, so I guess I'll just type this out myself. Okay, so e to the 2x. Actually, I can just copy the solution set from here. Very elegant. No need for any hard work. It's good. I don't very much like hard work, so very perfect for me. Um, so yeah, if format's still weird, I don't quite understand why, but I guess let's just let that be that for the moment. So obviously this Wronskian is going to be equal to matrix. Is going to be equal to a matrix of numbers, and this matrix maybe let's do this. Is this how you do matrix in LaTeX again? It's so long. Let me just quickly check. So obviously this is the matrix of the solutions. I'm gonna be honest, I'm really bad at LaTeX, latex, whatever. Okay, so I think this is the way to do it. So I believe there's a slash, and then brackets, and then so before the end. So then so I guess it kind of makes sense. The Wronskian kind of like I know what my problem with the previous like the previous problem is, but Okay. I'm having a little bit of a formatting error. That's good. The reason I started doing it this way is I also just kind of wanted to learn LaTeX, and I guess it's kind of helpful to be able to like format things in general. Because I mean, I guess it's pretty plainly obvious that like any type of mathematical or stuff work that you're doing, it's gonna be LaTeX that you're gonna be using. And okay, I'm not sure why this doesn't work. I thought this would work. But I think you guys get the point. You just take the Wronski. This does not look good, so I need to figure out. Oops, let me just put my computer on charge. Okay. See if this fixed it. No, it did not. Yeah, it's like weird. This I oops. Let's not do that. So anyway, I think you guys get the point. You just use the Vronskian but oh, it worked. Finally. Okay. So yeah, the Wronskian, what's very interesting is let's say you have three solutions. Um, so you go from you go obviously from you get a 3 by 3 matrix. If you have if you have four solutions, you get a 4 by 4 matrix. Um, but yeah, it's pretty cool. This is, I guess, a nice little solution, and we just need to compute whether this becomes zero. So let me just look at it real quick. This is like a lot of work, but let's just. But we know how to do the solution, so that's the important part. Um, but just looking at the expressions, they are probably linearly independent because you can't think of a constant c such that you can multiply one of these, get the others. So let's just say the Wronskian is not equal to zero. Wronskian equals. How do you do is not equals to in LaTeX? I'm pretty sure it's not just it's it's slash neck. I'm pretty sure neck. Neck is a pretty funny word. But So let's check if that worked. No, it did not work properly. So let's just okay. I'll just add another div. So I guess this is dually good. Ideally, I would be oh how do I do this in JavaScript? Rostering. Whoa. Yeah, the problem here is that it's processing the n as a new line character rather than a net character. So basically what we need to do is we need to convert it to a raw string. Which is kind of interesting. But the way we can sort of counteract that is we can do basically string.raw, and then the new line character will not be processed like a thing, but still it goes like this. But still we can just add this character. It's fine. I think we can just say it like this. We can keep it. It's not equal to 0, so it's independent. So it's independent. Cool. Uh, now let's look at the why does the Wronskian mean solutions are linearly independent? They're called linearly independent if there are non-zero constants such that C1 ft equals C2 gt. Sure, I can see that. If C1 f2, then C1 f'2. Ah, okay. Right. Right, this makes a lot of sense. So we'll just link this. We'll obviously copy this link to get our source, but let's add a sort of side note, and we'll basically just say like give props to this guy, this website, I guess. So we've just only put it in. So first thing we're gonna do is we're just gonna give it a class, which is side note. And then second thing we need to do is we need to probably style it a certain way. So let's just so let's call this div. The class name doesn't actually matter too much, so let's just go here. Let's add this little piece of thing in. But instead of we obviously need to rename this, so this is gonna be exercise. And let's call exercise 2. See if this piece of code works. No, it did not. Let's just make sure that this thing isn't inside this div. Or, oh, oops, oopsie doopsie. We did put it inside the div, not outside. So that'll be part of the reason, and then let's change up this CSS real quick. It sounds atrocious, but I guess we can always style it later, but we'll just add an A, add a quick A, then make this the href tag. At least this way we won't like forget about it later. So that tends to happen. If it looks ugly, I'll at least remember to fix it later. So that's good. Um, the Wronskian actually makes a lot more sense now. So, but TLDR, we'll just try to click TLDR real quick. So, I said real quick twice. So let's add a span, and then we'll set HTML to the span, and then we'll slash span on this side. So, okay, I don't really know. But so TLDR, it's just some simple HTML. So let's just do some more latex, obviously. Oops. Don't know where that came from. And then, so it just basically needs to be like, we need to basically say that since, how do you do text and latex again? Oops, this is meant to be inside the A. So, it's here. Um, so since f of g of x equals times c1 plus g of x times c2 equals 0. But why does it take the sorry, why does it take the determinant here? That's a question. So why the determinant though? Like that's my question. So obviously you have some functions. You take the derivative. You have get a linear system multiplied by the constants is equal to 0. And we're basically just asking like, is there a is there a is there a s- is there, does there exist a C such that C equals 0? Apparently from linear algebra, system AC equals 0 only has a trivial solution C equals 0 if and only if determinant A is not equal to 0. So if and only if determinant A equals 0, there exists a non-trivial C not equal to. Ah, okay, I understand now. Okay, so then obviously if this is true, then uh So then differentiating, this must also be true. This is just to sort of gain in our memory. So this makes actually a lot of sense. Fx times c1. Do I need the times? Oh, let's just get rid of the times. Of course, this is something that I keep over from the days when I used to input this into stuff like on I don't know like Wolfram Alpha and stuff, and it wouldn't recognize when you put like even my calculator, you don't put multiply, it doesn't recognize that that's multiplication. But LaTeX is smart. LaTeX is smart enough to not even need that. Just recognize that anything by default, if you have it in this format, it just takes as multiplication, which is very, very brilliant actually. It's kind of cool. So then obviously let's look at I'm just gonna copy paste this matrix in there for a second, but I'm just gonna use it to sort of just make sure I have the syntax right. Okay. Just put it here. So let's just get rid of this first part here. Okay, so let's begin the matrix. So our matrix should only need really two entries. So we don't need this middle row at all. And in fact, we don't need this part of this last row, but we just keep it for now. So let's just start by removing this e to the negative x. Let me just make sure it rendered properly. Okay, cool. That looks good. Okay, so instead of x squared e to the 2x, it should be f of g of x. So that's pretty simple. Write out g of x. This one should be f of x. This is obviously f prime of x. And then this was obviously g prime of x. And then now we have this matrix. So then we can construct. So we need to add some sentences here. Then we can construct this matrix equation. So obviously there's a couple of things we need to do. So we need to show that there's a constant matrix. And then let's add a matrix called P matrix, and then we'll change the constants to constants. So let's just do that. Oops, I must have done something wrong, clearly. But I don't quite understand exactly what's wrong with this equation, so let's just look at it for a second. So okay, it'd be kind of sick to be like, like kind of old people are like kind of lucky. They have a lot of good stories to be able to tell. What do we have to do here again? Just remember, it's string.raw, right? Let's try that. Really not rendering properly. I think it might be due to escape characters. I don't exactly know why. Raw. Let's try string raw. It's kind of like sometimes it can just be like a multi-purpose solution to a bunch of random stuff, and this time too. String.raw just comes in clutch day after day, I guess. String.raw is clutched up for me a lot. Especially if we don't know what to do, just try chucking string.raw in there, and sometimes it works. Okay, so this isn't formatted great, but I also made a couple typos, which is kind of good. So then we can construct this constant equation, and then obviously this equation has to be equal to 0. So and then I can just say this is only true if. So let's now just take the true if string.raw is like really weird in JavaScript, even though just the way it looks very weird because like it's like you just put string.raw and then you put a legitimate string. It just looks really weird. JavaScript. JavaScript is also a weird language, so I guess it kind of makes sense. I should also use backticks here instead of always use backticks. Yeah, maybe not always, but sometimes you can use backticks. Okay, so this is only true of the determinant of f, and it's just so just think about it logically. It's only true if the determinant uh it's only true if the determinant is so if equal to 0, then there exists a non-trivial solution. So it's only true if the determinant is equal to 0. And I'll just that kind of makes kind of makes sense. But yeah, let's just say true. Oh, 0. Okay, cool. Um, that brings up the question, like, why is that only true if the determinant is equal to 0? So apparently the rows of n can be rows of a. I looked it up. The rows of a can be thought as n vectors in n. Those are linearly independent. Then no combination of them gives 0 except the trivial combination. Okay, but this is like just kind of circular reasoning. Yeah, apparently it's just a linear algebra fact, and there's probably some intuition, but to be honest, I'm like a little bit tired now after doing 2 problems. So we can, I think we can, I think we can determine whether stuff's linearly independent kind of pretty well now. It's just pretty simple. Just put it into the Wronski and plug and shove. Install. Install. Okay. So there's a couple of other questions. Find a general solution for the given differential equation. You know what?